Now, the problem is you don't just use your brake once on a trip, you'll use them often, right? They're used approximately cyclically. You start and you stop. So, if that's the case and you stop too often, then initially the heat that's generated during use is going to exceed the heat that's lost between the uses. That's actually pretty much always true. If the temperature of the air outside is constant, then you can generate heat, but you can't lose it and get back down to a temperature that's less than what you started. You can lose almost exactly what you gained, but you can't lose more than that unless the temperature outside were to drop. Now, the peak temperature then is going to rise after each use. You're gaining more energy than you lose. On the other hand, the higher the temperature gets, the faster that heat is lost. You might remember that from previous classes, and we'll see an equation that describes that. And so eventually, the peak temperature is going to be high enough such that the heat that's lost between uses and the heat generated each use are almost exactly equal. And so at that point, you're kind of reaching an equilibrium where you do lose just about as much heat every time as you gain. And you're going to approach this asymptotically. The peak temperature is approached as an asymptote. So let's see how this works, and let's find out a little bit about what that asymptote is going to be for brakes that are used cyclically. Now, here's an example graph that I found at this website. This is an example of aircraft brake temperatures. So this is time on the horizontal axis, and here's the temperature. And you can see its first flight, it's taking off, and there's a little bit of braking that goes on, presumably when it's taxiing. But then when it's in the air, it cools off pretty rapidly and gets almost down to the temperature it started at. Now, when it lands, the brakes spike in temperature. You can see the temperature in degrees Celsius. This thin line is the disk temperature, and the indicated temperature is probably some sensor that's located nearby. When you're taxiing in, it starts to cool down, and when you taxi out, it gains heat again, but during the flight, it cools down again, and oh, look, your temperature has increased from the last time you took off. And then at landing, it spikes again, and that's higher than the previous landing temperature. But you lose heat faster when you're hotter, so you can see that it's losing heat at a certain rate here. It loses more heat in the same amount of time here because it started at a higher temperature. And so it's approaching this asymptote of a maximum temperature, and we're interested sometimes in what that maximum temperature is. Now here's the equation that describes the temperature of a body as a function of time. So this is the temperature at time t. And here is the ambient temperature, outside temperature. Temperature at time t is equal to the ambient temperature plus the difference between T naught, that's its initial temperature and the ambient temperature, and a decaying exponential in terms of this constant beta, which I'll describe on the next slide. I just want to pause for a second to see what that looks like and think about that. So let's look at that equation. What is the temperature at time t is equal to 0? Well, it's going to be T infinity plus, well, whatever this is, but keep in mind this is e to the negative bt, so e to the negative 0. E to the 0 is just 1. Anything to the 0th power is 1. So we're going to get plus t naught minus t infinity. And so these t infinities cancel out. And that's why this temperature here is called T naught. It's the temperature at time t is equal to 0. Now, the temperature, if you let it cool for a long time, infinite time, is T infinity plus, we've got our T naught minus T infinity, and we've got e to the negative infinity. Well, e to the negative infinity is going to be 0. It's a decaying exponential. So this whole thing gets wiped away, and we just get the temperature at time infinity. So that's why it has these symbols. T naught is the temperature at time t equals 0. T infinity is the temperature after infinite time. It's the same as the ambient temperature. It's going to come into thermal equilibrium with the environment. Now, what about this constant beta? Beta here is given by this expression, where h sub r is the radiative heat transfer coefficient, and Fv is a ventilation factor, Hc is a convective heat transfer coefficient, A is the surface area of whatever object is shedding heat, On the bottom, we've got mass and the specific heat capacity. Let's break this down a little bit. So up top, we have a term that describes how fast energy is being lost, and the bottom is how much heat energy needs to be lost to cool down. So the larger this whole number is, the faster that the object cools down. But all those coefficients on top depend on how much hotter than ambient temperature the object is. This book writes it as the temperature rise, but more specifically, it's the difference between the initial temperature and the ambient temperature. So here we have two curves, one that expresses the convective heat transfer coefficient, and this one is the radiative heat transfer coefficient. So let's take a look at this left plot right now. You can see that as temperature increases on the horizontal axis, then your convective heat transfer coefficient increases at least slightly, and it asymptotically approaches around 2.5, I'd say. And then your radiative heat transfer coefficient, that one keeps on going up as you get hotter and hotter. Now, there was also this multiplying factor that was applied. It looks like the convective heat transfer is going to be less important, but it turns out that the FV is going to get multiplied by this HC in the equation from the previous slide. So as the air is moving faster and faster across the surface that's dissipating the heat, well, this multiplying factor FV increases as well, up to an asymptote of around, it looks like, 7 or so. So let's do an example problem. If the maximum allowable temperature of the brake material is 700 degrees Fahrenheit, and each brake on this truck that we were studying in the last problem has an effective area of 150 inches squared, how often can the truck make these stops without overheating the drum brakes? And we need to make an assumption about the forced ventilation velocity. In order to solve this problem, let's draw a diagram of the temperature as a function of time. So on the horizontal axis, we'll have time, and on the vertical axis, we'll have the temperature of the brake. And we're assuming that we're making these stops cyclically. We're driving for a while, we're stopping, we're driving for that same amount of time, we're stopping again. That amount of time every time is we're gonna call that delta T. And we want to know how long those cycles can be so that we're just barely on the verge of overheating. So what does one of those cycles look like? Well, we're going to start at some temperature, some initial temperature after driving for a long time. I'm not sure what this is yet. It's not going to be the same as the ambient temperature. The ambient temperature is the outside temperature of the air, T infinity. It's not going to be all the way down there. We're not going to get down to there every time. And we are going to break this point, and so our temperature is going to rise. It's going to get up to here, our maximum temperature. So here's what our temperature does. It starts off here, and then it rises. Straight line, it jumps up to our maximum temperature. This rise here corresponds with this equation. The change in temperature is E over CPM. So when we break, instantaneous change in temperature delta T is equal to E over CPM. We already calculated what that was. That was around 300 degrees Fahrenheit for our truck. Every time it stops, it gains 300 degrees Fahrenheit temperature. After we stop, we start driving again and we start cooling down. So that's the heating phase, and then we cool down. It's going to look something like this. And if we continued driving, we would asymptotically approach T infinity, right? Way out here, we'd approach T infinity, but we're not going to do that. We're not going to get all that way down. We're going to stop again after delta T. We're going to stop again right here. And then our temperature is going to rise, right? It's going to go back up to T max. And that's what we're saying, is that we go through these cycles. We stop, we cool down, and we stop again. And temperature is so high that our cooling is so fast that within this amount of time, we cool down by exactly as much as we gained in temperature whenever we stop. So what's that condition? Well, this here, our T naught is equal to T max. And this temperature here is the temperature at time delta T. By the way, I should mention, this curve here corresponds with the temperature as a function of time is given by this equation right here. That's how I know it's going to have this sort of shape and asymptotically approach T infinity. So what's our condition? We know that the change in temperature every time is equal to our initial temperature, which is actually T max, but I'll call it T naught. We know what that is. It's equal to T max, minus the temperature here at time delta T. Temperature rise here is equal to the temperature drop as we cool down. So we know this. We know this from before. We can calculate what this is in terms of delta T. Let's go ahead and plug it in and see what happens. So we have T naught minus temperature as a function of delta evaluated at T equals delta T. Let's simplify this. We can write it out that way, but then we can group terms. All right, and what are we after? We're after this delta T here, so we need to solve this. So this means delta T over T naught minus T infinity is 1 minus e to the negative beta delta T. I think we're going to want to add e to the negative beta delta T to each side. And we'll subtract this from both sides. And then we need to take the natural log of both sides, I think. Logarithm. But the logarithm of this, the reason we did that is because that's just negative beta delta T. And so we can just divide both sides by negative beta. All right, so that is the amount of time such that this thing cools down by exactly as much as it gains every time we stop. So let's evaluate this. We're going to need to know beta. So that's going to depend on HR. Let's find out what that is. That is our radiative heat transfer coefficient, and it is a function of what the book calls the temperature rise, but it's the initial temperature minus the ambient temperature. So that is, in our case, the initial temperature minus the ambient temperature. Well, the initial temperature is T naught, that's 700 degrees. It's the maximum we're allowed to get up to, minus the ambient temperature of 100 degrees. That's 600 degrees. So we're going to need to look up the radiative heat transfer coefficient when our temperature above ambient is 600 degrees. So at 600 degrees here, we have a radiative heat transfer coefficient of about 8.5. What are the units on that? Well, the units are, it's written very small. I'll copy them down. 10 to the negative 6 BTUs per second inch squared degree Fahrenheit. All right, what about this FV? That's the multiplying factor. That's the factor by which we're going to multiply the convective heat transfer coefficient. The faster the air is moving, the faster it gets carried away by convection. So we are going at about 100 inches, 100 feet per second. That's what the problem said, 100 feet per second. But we said this was a drum break as well. And I want to be somewhat conservative, so I don't want to use 100 feet per second. But let's say, that we have a little airflow through there and it's about 20 feet per second is what we'll use. So our multiplying factor FV, I'm just going to choose as 4 to be somewhat conservative. It's not going to be all the way out here at 100 feet per second. But it's not going to be 0 either. So FV is equal to 4. Our convective heat transfer coefficient is, well, at 600 degrees, HC is about 2.5. Again, same units. Our area, that was 150 inches squared per break, but we've got 4 breaks, so really it's 600 inches squared. And we already calculated the product of the mass and the specific heat capacity before. MCP, that was equal to 4 BTUs per degree Fahrenheit. All right, if we calculate this out, we get beta is equal to 0.002775. And what are the units? Well, the units should be 1 divided by time because e to the negative beta t needs to be dimensionless. Let's double check that. Up top, we're going to have, well, this is all in BTU per second inch squared degree Fahrenheit times our area. That's going to get rid of our inches squared. And then on the bottom, we have BTUs per degree Fahrenheit. So that's going to get rid of these, and we're left with 1/seconds, which we should have. All right, let's plug that into our equation then. Plug in all the numbers. We've got delta T. This here was a temperature change of 300 degrees every time we put on the brakes. T naught minus T infinity, that was 600 degrees. We calculated that. So this here is just 1/2, and 1 minus 1/2 is also 1/2. So we have the logarithm of 1/2 over negative 0.02775. And why is it negative? Well, the natural logarithm of 0.5 is going to be a negative number, so this is going to turn out to be a positive number, and it turns out to be around 250 seconds, a little bit over 4 minutes. And so even if we were every 4 minutes to go to a complete stop from 68 miles per hour and start again, get up to 68 miles per hour, and 4 minutes later, go back down to 0. If we were to keep doing that repeatedly, we'd be just on the verge of overheating our brakes at 700 degrees Fahrenheit. Let's hope that if we're on highway, we don't have to go that fast and slow down to a complete stop every 4 minutes. That would be an awful long trip. I think that we're pretty safe for normal conditions.